So when talk about semiconductor, the first semiconductor come to mind for everyone is definitely silicon, and then we have a great TSMC users. So, but does anybody heard things about silicon laser diode? Probably not, because there's no some kind of stuff. And there's two reasons. So the first reason is that the silicon is interleaving material. And if you ever took solid state or probably you should know what is interleaving material. But I'm not repeat that. If in a band structure, the lowest energy for the conduction band, the highest energy for the lowest band, stay on the same K, and it must be K equal to 0. So in this case, this material is called the red band gap material. And the transition between the conduction band and the valence band edges doesn't need to involve incorporation of the form. So it still satisfy the conservation of. However, for some materials, actually many materials, many semiconductor materials, the lowest point in the band edge is not the K equal. So while you excite some electron at the top, it's going to populate the energy, lowest energy. So because the energy electron is at some non-zero K, and you hold some 0K, due to the conservation of momentum, you must incorporate something with momentum going forward. So this makes this process still possible, but unlikely. That's just like your the rectangular material, just like a man walking outside and encounter a woman. Okay, this process is very high likely. But although in NYC probably a little bit unlikely anyway. But in the rectangular material means that a man need to encounter a woman, and they have the same weight. So this the third condition make this still possible, but this makes the probability much smaller than it should have. So we just assume it doesn't happen. So in the rectangular material need the incorporation of a right photon at the right space and the right time. So the emission between in the rectangular material, the rate is pretty lower. So that means we need a direct rectangular material to build the semiconductor laser. And the second reason that we don't have a silicon laser diode is because they are the same material with no band gap difference. So the best you can do is has a p-type GaN, n-type GaN, heavily doped or undoped. You cannot really feel an energy difference at some specific position. So when the electron injected or hole injected from both sides, it's difficult to build up a region with simultaneously a high electron and high hole concentration. So the recombination rate is not high enough, or the population inversion is difficult to achieve. So these two may make the semiconductor laser not possible with the platform of the silicon. So we need to turn to the semiconductors with the red band gap material and the tunable band gap. And that counts 3-5 semiconductor or compound semiconductors. So 3-5 semiconductor means it's a compound semiconductor with a group of elements 3 and a group of elements 5. So according to, it's further classified usually according to its 5 elements. For example, we will call it free nitrile, free phosphide, free arsenide, and free antimony. And we are running out of elements. So usually for these 4 elements, and according to its corresponding free elements, it might further into aluminum nitride, gallium nitride, indium nitride, aluminum phosphide, gallium phosphide, and indium phosphide, etc. And they have a lot of them are the red band gap material. For example, for free nitride, they are all the red band gap material. And the alloy between them For example, aluminum gallium nitride, indium gallium nitride are also all the remaining material. So this makes this material appealing and interesting than other materials. So standards the free phosphide, but you need to see that the free phosphide is only direct for indium phosphide. For aluminum phosphide and the gallium phosphide, they are in the remaining material. Okay. And for free arsenide, the aluminum arsenide is the remaining material. But gallium arsenide and indium arsenide are the remaining material. And the antimony, the aluminum antimony is in the remaining material. But the gallium antimony and indium antimony are remaining materials. No particular reason. You can just accept the truth, the boundary of our world. Anyway, and then they have a different bandgap, but the bandgap usually has a more clear trend. Those with smaller or lighter elements, with aluminum, usually has not usually, always has a larger energy bandgap. For example, the aluminum phosphide, the bandgap is 0.21 eV, and the gallium phosphide is 2.7 eV, and the indium phosphide is 1.35 eV. And there's a reason, like we spent some time in the solid state physics, so probably not gonna repeat that. Probably you can just accept that if you don't have no idea why. And this bandgap is strongly relevant about what wavelengths it can be used to build such semiconductor lasers. And the relation is just like this, because the lambda is C over mu. The mu is frequency. And we can do the same operation times constant divided by E. And the mu also times Planck constant divided by E. And H mu divided by E is bandgap in electron volt. And these three are all constant. After transformation, calculation is equal to 1,240 nanometers. So, for example, if you have a material with 1 electron volt bandgap, that means its absorption age is around 1,240 nanometers. Or we can do that with the reverse way. If we want to make an emitter at 400 nanometer, what material you should use? So we can make the 400 nanometer here, build it and calculate that. So the value will be 1,240 divided by 400 nanometer. That will be around 3.1 eV. Okay. So do we have a material with 3.1 eV? No. Okay, you might have something between gallium nitride and the indium nitride to satisfy to make an emitter at the 400 nanometer. So for short wavelength materials, you have no more. You don't have any choice. You need to use the free nitride. All right. So to classify, besides classify them with your element in the bandgap, we have another way to classify this material according to its crystal structure. So let's consider you have so many orange. Just you see in the fruit shot, and you put in the orange closely one by one. So you build a hexagonal array like this. So let's call the bottom level, the position called A position. Then you need to build the second level because you have so many oranges there. Okay, so it could be either in the B side or in the C side. B side, that means it's in the small gap, but with the tip point upward. But the C side is the point, you have the tip point downward. So they are not equivalent. Although you see that, oh yeah, I can change the figure 180 degree, they will be equivalent. Yes, you're right, but let's assume it's not equivalent yet because we haven't put a third layer. So let's assume we already put your second layer on the side. So you want to put the third layer of now we have the two choices. Since you cannot put the orange at the same side, it will be not stable. So you have to either put it back to the A side, the exact position of the first layer, or put it in the C side that I haven't used it. Alright. So your packing sequence could be A, B, C, or I mean only the third layer, or A, B, A. And these two give you different crystal structure. So if you do the stacking around the ABA, then second layer also B. So it's AB, 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 AB. You get a crystal called the hexagonal closed pack structure crystal. This crystal is the structure of a free nitron. And if you put the structure back to C, and the fourth layer return to A, and circle it. That means your structure is ABC, ABC, ABC. Then you get a cubic structure if you see your agent from a different view. So this kind of structure has a different name. It's also introduced in the diagram. The ABC structure is called FCC. And the ABAB structure is called the hexagonal crystal. They are different class of materials inside structure. And you can see that they are a set of mathematical points if you put the right coordinate. Then put something at that mathematical point. Just like those things. These things are mathematical points. But you can put a man on it. You can also put a girl on it. Or just put your bag on it. So that's the difference. The position is only a coordinate. And but you can put anything on it, and that anything could be 2 atom or 3 atom. It's not limited to one atom. So that gives the different structure of the three kind of most common crystal structure: silicon, zinc blende, and wordline. The first one is the FCC structure, but at each point you put 2 identical atoms. You see this in the dashed red line is a dumbbell, and put that along the 111 direction. Then repeat that. So for this FCC point, you put a dumbbell of these 2. And for the point here, you put a dumbbell between these 2. So then you build a structure called the diamond structure. It's the lattice point of FCC and the asymmetric semiconductor atoms. If you put carbon, then it's diamond. If you put silicon, then it's silicon. And the same as the germanium. Okay. But if you put the 2 different atoms with put the 2 different atoms at the FCC side, then you get this blend. It's usually one free level, one in the group 3 and one in the group 5. For example, you can put one with gallium and the other one with arsen. Arsen or arsen anyway. Yeah. Then you have gallium arsenide. Similarly, you have indium phosphide (IMP) and others. For most of the free fine materials, not including nitrogen, are all in the zinc blende position. Yeah, so this is called a special name called zinc blende because the most common material, the first encountered material in this structure is the zinc blende, DNS. And the third one is called wordline. It is the HCG structure, and with the free fine dumbbell in the principal acid. For example, you may have one with gallium, and the other one with nitrogen. So you have a gallium nitride. Similarly for aluminum nitride and indium nitride. And this builds the free three types of semiconductor material nowadays. The first one is we also know as the first, but this is just a name. First generation of semiconductor is usually used in the integrated circuit. And the second one, based on the nature, it usually happens with the power amplifier, the read emitters, and the communication lasers. And for the group of nitrides, usually is the most popular one recently. Somebody called it this third generation semiconductor or 第三代半导体. But I think this is the commercial name, it doesn't have any physical meaning. But recently it's very useful in power devices like electric car. How do you turn your control your power or your Tesla efficient? You need the wide bandgap materials because you need this kind of wide bandgap material to handle such great large current and high voltage bias. And recently, UV light is also a popular topic for the nitride batteries. So since you have a crystal, you have a lattice constant, and it evaluates the size of your lattice. So this field is I call the world map of the compound semiconductor. It's a scatter plot between so many kinds of semiconductor, and the y-axis is the bandgap of this material, and the x-axis is the lattice constant for the crystal. But however, you need to notice that they also score the lattice constant, but they have a different structure. So for the worst type, it refers to the A here, because you have a constant A and a constant C, so you actually have two lattice constants. For convenience, we usually in this figure we only noted the A constant here because that's the common one. It's rarely used along the C constant anyway. And then you have another region here. This is because QB you have the three equivalent lattice constants, so you only need one number A. Alright. So those points are simple element, gallium arsenide, indium arsenide. However, you might avoid my example, you could put 50% gallium arsenide and 50% indium arsenide, and pushing the material in at the same time, so it's 50%. So if you get a 50% like an Indian, 50% Indian, 50% gallium arsenide, your bandgap will be something in the middle. So you should get a trace about this material. So this trace is the material of the Indian gallium arsenide. For each composition, you also get the lattice constant and the material bandgap. And you need to profit some of them. Okay, so this will visualize how we decide what material to use while building the semiconductor. For example, we have now an iPhone. The iPhone has a Face ID that will scan your face to get signal. And the wavelength it uses is 980 nanometer VSO. And why 980 nanometer? Because it doesn't have a strong background in the air, so you might get a better signal. Okay. So since we want the wavelength to be 980 nanometer, so we know that it's probably around 1.x, yeah, or 1.1 or 1.2. Okay, so probably here. Then you need to use the material along this line. So you have many choices. You could be this point, a gallium arsenide with 20% indium, or INGASP. What is that? We will talk about that anyway. Some alloy between indium, gallium arsenide, and the phosphide INGASP with a specific composition. That's here. Okay. Those two are both possible, but we choose gallium arsenide because gallium arsenide is stronger. indium phosphide is very fragile. So if both platform works, we might use gallium arsenide, yeah, because for practical reasons. So in the real world, in the iPhone you have, the Face ID indeed has a substrate of gallium arsenide, but its active region is indium gallium arsenide, since it's still possible to grow that. Okay, now we have another example of a laser. You might have a PS at your home, base station, and or even maybe you have a Blu-ray DVD. And the invention of the Blu-ray DVD, because it's the realization of the blue laser diode at 400.5 nanometer. That is a good, great achievement of Professor Nakamura. Because in the beginning we use the red laser, 935 nanometer for your Walkman, or probably you are too young for Walkman. At the beginning, the CD is read and write by red light, and the wavelength is 600 nanometer. So the record density is limited by your spot size. So if you have a shorter wavelength, you can record your CD with a smaller spot. So you can put even more things inside your one CD. Then you have a greater gain, since you have more documents and figure to use in your game. So it's very important to have a short wavelength by that time. But now we already put everything on the cloud, so this is not more an issue anyway. So if you let's go back to like for 20 years ago, we want to make a 4-5 nanometer laser. Then you see a 4-5 laser about 3.1. Then along this line, you only have a choice probably for indium gallium nitride with 9% indium. That would be a suitable material. And you want to pick a substrate through that. So the closer one will be the gallium nitride substrate. That's also a difficult topic by the time. Okay, so this is the property of the semiconductor laser diode. I'm gonna explain one by one. But while you're doing your homework or other things, that will be a good table. You don't need to find it all over the world. Yeah, you can definitely Google that, but different people may give me different number. Yeah, that will be pretty problematic. Okay, so that is that point. That figure pointed out the fundamental compound semiconductor about their properties, like lattice constant and the band gap. But we want it tunable. We don't want only 2 points on the same. We want a line between that, so the band gap can be changed according to its composition. So we have something called the Vgas law. Vgas law not a real physics law. It is not a great law proposed by a great scientist. It's just an empirical relation. It indicates that the band gap and the lattice constant of a alloy composition can be directly interpolated 内插. So for example, for indium gallium nitride with the X composition of X indium and the 1 minus X gallium, the first order approach is to do a direct X times band gap of indium plus 1 minus X band gap of gallium. So the band gap of the indium gallium nitride can be tuned by tuning the composition of X. Similarly for your lattice constant. So let's put another example of INGASP. You see that the indium and the gallium are group free, and the arsenide and phosphide are group 5. So because it is 1 to 1, so if gallium is X, then indium is 1 minus X. Then if arsenide is Y and P is 1 minus Y. So the lattice constant of INGASP will be the x times y, the lattice constant of GAS. Okay, x, y, GAS. And the 1 times x, 1 minus x times y times INAS, IN 1 minus x, AS, y, similarly. So it's a directly linear, the linear combination of the lattice constant of the single materials. But since if you see the figure here, it's not really a straight line. It's close to a straight line, but not definitely a straight line. So a linear feature, a direct linear feature between these two, probably not precise enough. Although it is not too bad for gallium arsenide and indium arsenide. However, for indium arsenide and the indium platinum, the direct line probably not a very good approach because the fact is this time. So from the perspective of curve fitting, you need to add more term. So you might have a second order term called with B called point parameters. Yeah, for indium the point parameter will be 1.21 dB. Then you need another term. We take the positive, we have a minus here because we let the B to be a positive number. That sounds more comfortable. So it will be minus bx times x times 1 minus x. Yeah, so this is only approaching. So if you read the paper, they will have a more clear estimation and remind that the point parameter basically is the second order parameter. This direct linear combination works for the many parameters. Like the most important is the band gap and the lattice constant. But however, there's so many material parameters. They probably doesn't follow the same rule. One exception, or actually it's not exception, is the effective mass. Effective mass is a linear combination of its inverse number. The reason is that the effective mass is defined by its band gap in the reversed way. Since you already estimate your band gap with the linear combination with E, surely you have to do the same way. So the effective mass is evaluated with in the inverse value. That's the reason here. And another important exception that you need to take care of is you need to do this linear combination only when those two materials are all the remaining materials while you do band gap. So the most common example is gallium arsenide and aluminum arsenide. This is the band gap of the gallium arsenide. It has the lowest band gap at the gamma value, that's the K is equal to 0. And for aluminum arsenide is X larger than 45%. The lowest level is in the L value. Anyway, something not the case not equal to 0. Because the band gap is defined between the lowest energy of the lowest energy minima in the conduction band and the highest energy in the valence band. So the EG is defined here, not here. So you can see more clearly this is the band gap and this is the composition of the aluminum. So when the composition of aluminum is low, the lowest energy is dominated by its gamma level. So if you only see the gamma level energy separation. Gamma level, yeah, it's pretty close to the red line. Yeah. Probably a little bit boring, but it is okay. And if you see the X value, so the arsenide, the lowest one is X value, yeah, the figure says the X value. So if you only see the X value, for aluminum arsenide, it is lowest at the X value. But for gallium arsenide, it is not. So the band gap is the lowest curve of the energy separation. So the band gap is actually these two lines. So if you directly do V-gas law between the gallium arsenide and the aluminum arsenide, your composition is along this line. The black dashed line. Surely you will get the wrong answer. So it's important. So it is actually important to record the crossover of the two values. So we call this the direct indirect transition. That means under this position, the energy minimum is the set for the two values. So it eventually changes from direct bandgap material to indirect bandgap material, or vice versa, might be from direct bandgap to current material. So for gallium arsenide, this position is 45%. And that would also important parameter for the family of the aluminum gallium arsenide. And while you're doing the gas law of the bandgap, you need to do the two segment. For example, if you're looking the bandgap of the aluminum 20%, you need to do the linear interpolation between gallium arsenide and the outgas. It's 45% aluminum. Similarly for this one. So you might encounter one of them in your